They have to both increase, but this one increases more. It's the only way that those two things can be true, right? This has to start, sorry, this should be a -1. This has to start much larger and end up much smaller. So which one is more sensitive to temperature?
So how did you know that K started at the top?
Okay. I haven't answered the question yet. All I know is one of these things, right? So now I have to come back into here, and I see that E low is equal to E1 plus some number greater than 0. And E high is also equal to E1. So E high minus E low is just equal to E2 minus E negative 1, which is greater than 0. So E high, no, I got it backwards somewhere.
It's less than 0.
Yeah, help me out. Oh, I know it's less than 0, but where did I make my mistakes?
Because E low is E1 plus E low minus E high, not E high.
Yeah, thanks. You got it. Yeah, so this becomes negative times that. Yeah.
So is there a negative there?
Yes. E high minus E low means that this will be negative when it moves over. So you get equal to -1 times E2 minus E negative 1. Okay. Yeah, so E low greater than E high. Any questions? So let's review that first problem. It started with, here's a mechanism, derive a rate law. Then we moved from, we have a rate law, what's the effective rate constant? Is there an effective rate constant? And then taking that effective rate constant with some assumptions and with some extra information, we can determine the relative magnitude of the activation energies involved in the reaction. Okay. Problem 2.
That's a good question. So at the lower temperature, K2 is much smaller than K minus 1.
Yes. So at 0, this is smaller than that.
Okay, so then the activation energy at a low temperature, E2 is still smaller than...
The activation energies do not change with temperature.
Okay.
Activation energies do not change with temperature, at least not in this course. In reality, they do change, but they change a very small amount. Otherwise, you'd never get an Arrhenius equation, right? Because Arrhenius says, if I rearrange this, I'm going to get a constant slope, which is equal to the activation energy, with some other constants.
Wait, so the activation energy, like larger activation energies, are more sensitive to temperature?
No, I started to say that, and I might have said it as a mistake. Rate constants which have larger activation energies are more sensitive to temperature. So sorry if I said activation energies are more sensitive. It's one of the, it's hard to say it right out loud because it's, but this is what you see. The rate constant is changing by a larger amount because it has a higher activation energy. All right, and like I said, that would be worth 30 points.
Is that the hard one?
No. That's probably, come on. You didn't even have a design equation. There's no reactor in that. You think that's going to be the hard one?
Yes.
Okay. You wish.
Did you make the test already?
Which order? No. I have not made the test. Okay, so the liquid phase irreversible reaction, A goes to 2B plus C. Sorry, this one's also 30 points. So this reaction has been found to follow the unusual rate of formation of A, written as decomposition, but that's okay, given by this equation. Where XA is the fractional conversion of A, and your goal is to design a flow process meaning what reactors can I use? To achieve the fractional conversion equal to 80% with a minimal I'll put total reactor volume. So there's no limit on the number of reactors you can use. You just have to use CSTRs and PFRs. And the first question is, what type of ideal flow reactors would you choose, and in what configuration would you place them? Meaning that you need to tell me both the order and the volume of the reactors you choose. And of course, their type.
Okay.
I've given you all the information you need to solve the problem. So, make a Levenspiel plot. How did he know that? You have a question?
No.
You're going to say make a Levenspiel plot? Good. Because you're given this. You're never going to be given that for a real problem where I'm going to want you to derive that, right? So the fact that you're given rate as a function of conversion should be a pretty big clue that we're going to be solving this using Levenspiel plots, which is what type of solution? Is it numerical, graphical, analytical? Yeah, it's more or less graphical graphical solution. It's okay to make up your own words. Not on the test. So I flipped through this in vain. I don't see a plot. So how do I make a plot without a plot?
Guess and
This isn't a guess and check thing. That's an iterative solution. To make a plot, I just need to put some numbers in and get some data points. So what's a good data point to start with? First of all, what is a Levenspiel plot of?
You have to do 1 over
1 over
RA.
RA.
1 over RA.
I think it's negative.
That's right.
Yeah.
Versus X. Okay, can I make that plot? Are you sure? You think you're ever going to be asked to estimate a rate constant in this class unless I give you experimental data with which to do it? Just because it's a constant, you could put in 1 or 8 billion. Rate constants can be anything. Oh, sorry, I messed up. No, I didn't. No, this is correct. Sorry. Never mind. All right, so let's first take this and let's plot -1 over, or let's write out what is -1 over RA, right? So what is that? -1 over RA is equal to what? 1 over K. Everybody see what? and then back. Now without the -1 exponent.
Assume k is equal to 1.
Assume k is equal to 1. No, 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 no.
I'll negative k over r.
Do not assume k is equal to 1. So instead of plotting -1 over RA, what should I plot instead?
Negative k over r.
Okay. So how do I make a plot from nothing? Well, what's a good place to start?
0.
Is conversion bounded?
Yeah.
Yeah, so let's start with the limits of conversion, right? Okay, so when x is equal to 0, what is -k over RA equal to? Right, 1 minus 0 minus 0 plus 0. And when x is equal to 1, (1 minus 1 plus 5). So 5. All right, well that's a start. Any other data points that I should do? What else should I do to fill this plot out? Should I just do 100 data points?
You can probably solve for any zero stuff.
Solve